time to go back to work. So here we are. And today we start vector algebra. So how many of you at the moment? Let me see. 44 plus myself, and my second incarnation is upcoming, but slowly. Evidently, the second computer is slow a little bit. Anyway, so there's not enough people yet for me to talk much about the unit test on Friday, except that I'm telling you now that there are 3 groups, and some of you will have to write the unit test after the regular lecture time. The good news is that there's no lecture as such. You only will spend 15 minutes with me, 40 minutes writing that unit test, and 10 minutes setting up the file and uploading it. So even those of you who have to start later than usual, that would be after 4 on Friday, will have a free time before that. There's no lecture, so in fact, I hope that this is. I would think it's well compensated. The groups will be uploaded shortly. I'm still making small adjustments according to your schedules, because I know that some of you cannot do this after the regular lecture time on Friday. You have something else. Some of you, not all. So I am making slight adjustments, although basically those groups are by alphabet in my list, more or less. But in principle, there will be some little adjustments. I will upload the lists shortly after the lecture. I simply have to format the file so that it looks nice enough, so that you can find yourselves, so that you can understand what's going on well, and then that will be uploaded. Okay, now I'm going to switch off my camera because it is, as always, distracting for myself. And I will, let's see, adjust this chat in case somebody needs to ask something. All right, this is it. And there we go. So today we start vector algebra. Let me have a look at this. Okay, this. And something very light, like white. So let me just check that I can write. Everything goes well. Okay. So I might just as well erase this now. And before we start doing vector algebra, I remember perfectly well that last time, that is on Monday, I did promise to finish the last example properly, the last system properly. We started it sort of, kind of, but there was not enough time to finish it properly, so I promised to do it normally, regularly. So this was the system that we had. And the main thing was what to do with the ranks of matrix, I think, the main problem. Because Gauss method as such is not so bad. The problem might arise when we are trying to deal with the ranks of matrix. So at the moment, I'm doing one thing. I am starting already by exchanging the first and the second row already in the matrix, in the augmented system matrix. So remember, we wrote the matrix, and I'm writing the second equation already as first, because you know that was allowed, that was normal. 1 minus 1 minus 1 minus 1 and minus 3, and the first row as second row. So I'm doing it from the beginning so that those who had to miss last time can catch up with us. Now that was the first equation now is simply coming as second. Third equation, 8 coefficients, minus 2, minus 5, x4 is missing, and therefore the coefficient is 0. And then we have 3, 3, number 3 is missing, x3 is missing here, so we write S0 there, and we have F5, and then we have, of course, minus 8 and 7. Now this is the system matrix. Let's have the matrix, and let's see what we can do. So our aim was to create row echelon form. So basically our first aim, the ideal goal, it doesn't always happen. Ideally, we would like to have the identity matrix of size 4 by 4. In that case, we would have this unique solution. X1 is this, X2 is that, X3 is this, X4 is that. But the problem with this is that this doesn't always happen. It doesn't always happen, and we have to be satisfied with the reduced row echelon form, which is as close to the identity matrix as we can get. As close as we can get to identity matrix. That's the whole point. And so now what we do will be, of course, row 2 minus 5 row 1, going of course into row 2. So I am writing the matrix again. So back to my old device at the moment because I am at home, so it's easy to use that. And so we have still 1 minus 1 minus 1 minus 1 minus 3. And we have 0 now because we multiply by minus 5 and add exactly because we want to make this 0. I keep repeating myself, I know. I repeat the same things over and over, but the purpose of that is to remind you. All right, 49 of you, still not everybody has written their name in the chat. Please do it. Please remember to do it because otherwise I'm assuming that not everybody is listening to me at all. Make sure, because if you do it too late, you will be counted as late, and that will affect your attendance. If you are more than 15 minutes late, you're automatically counted just half a lecture. You are marked as late. All right. So minus 1 times minus 5 is 5. Added down is 6. Minus 1 times minus 5 is 5, added down to minus 2 is now 3. Again, 5 plus 3 is 8. Minus 3 times minus 5 is 15, plus 1 is 16. And if I remember correctly, I think we got all the remaining rows that were the same, if we did things correctly. So let's see, row 3 minus 8, row 1, because we want to get rid of the 8. So 8 minus 8 is 0. Minus 1 times minus 8 is plus 8. 8 minus 2 is 6. 8 minus 5 is 3. 8 minus 0 is 8. And minus 3 times minus 8 is 24. 24 minus 8 is 16 again. And finally, the last row, row 4 minus 3, row 1. We did it. So that's, again, we get a 0 in the first column because minus 3 plus 3 will be 0. Then minus 3 times minus 1 would be plus 3. 3 plus 3, 6. 3 plus 0, 3. 3 plus 5 is 8. And minus 3 times minus 3, 9. 9 and 7 is 16. And yes, indeed, what we have now is 3 identical rows. You will have noticed, some of you will have started the home assignment already. You will have noticed that some of you have these strange situations. Basically, you have to investigate how to orientate yourselves in these strange situations, these new situations. What we see is if I take row 3 minus row 2, I get all zeros. If I take row 4 minus row 2, I get all zeros. And we might use the equivalent sign between matrices, not equality, because they are not equal. And so what we have is 1 minus 1 minus 1 minus 1 minus 3, 0, 6, 3, 8, 16. And then we have 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0. Okay. So what we see at this moment is that we have a matrix of rank 2. Remember what rank was. Rank of a matrix was the maximum number of non-zero rows after we have completed Gauss transformations. these row operations. Of course, we can simplify. This is simply the row echelon form. It's not reduced row echelon form. To make reduced row echelon form, we actually need 1 here instead of 6 and 0 above. Well, that's something that we can do. We can divide the second row by 6. If we divide the second row by 6, we have, okay, 1 minus 1 minus 1 minus 1 minus 3. Repeating myself, so we have 0, we have 1, we have 1 half, we have 1 half, we have, okay, or we could have 3 over 6, but let's have 1 half. We have 8 over 6, that's 4 over 3. 16 over 6 is 8 over 3 after simplifying, although over 6 would have been good enough. 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0. Vertical line to make sure we understand what is what. And now I can subtract first row minus second row, row 1 minus row 2. The purpose being, okay, let me get the ink, it will be yellow. The purpose being making a 0 there above the leading coefficients. So the reduced row echelon form is actually, the aim is to make 1, all the leading coefficients in each row. The leading coefficient is the first non-zero coefficient, making all those leading coefficients equal to 1, and then all the coefficients above should be equal to 0. Why? We will see in a moment why I do insist on this, why this is actually the best thing that we can do with this. So what we have now is, okay, I'll start from the bottom this time. I'll have 0, 0, 0, 0, 0. I will have 0, 0, 0, 0, 0. I will go back to the common denominator. So 0, 1. 1 half is 3 over 6. That's when we divide it by 6. So this, we had 8 over 6. We had 16 over 6. This is for the sole purpose of being able to write things on the common denominator later. And here we will have 1. So minus 1 plus 1. Actually, not minus row 2, but plus row 2. I'm sorry, plus, plus, plus. Because now when I add 1 plus minus 1, we get that 0 above the lower leading coefficient. Now when we add, we get minus 1 plus 3 halves is simply minus 3, not halves, but over 6. Minus 1 plus 8 over 6. Minus 1 is 6 over 6, so we only have 2 over 6 remaining. And minus 3 is 18 over 6, minus 18 over 6, plus 16 over 6, that would be minus 2 over 6. Why am I doing it like this? Now let's see. What we have, we don't have to write it like this, but what we actually have from that system is now x1 minus 3 over 6 x3, because x2 is missing there, plus 2 over 6 x4, and on the right hand side we have simply minus 2 over 6. And the second row, in the second row we have x2, because x1 is missing, plus 3 over 6 x3, plus 8 over 6 x4 equals 16 over 6. And then we have just 0 rows, meaning absolutely nothing. So this is the system that we have, let's say, in our mind. Generally, we don't even write this. But now what we see is the rank of the system matrix A is 2. The rank of the augmented system matrix is also 2, because the number of non-zero rows is the same. If we only take the left side to the left of the column of the vertical bar, and if we include everything it's still the same rank. It's still the same rank because nothing is added down here. The rank of the augmented matrix does not increase, but the number of the variables is 4 unknowns, which means 4 minus 2 is 2, two new constants to be chosen, which means I could say let x3 be equal to A, let x4 be equal to B, and then we can express x1 and x2. So x1 would be everything on the denominator, 6. Now, moving this here, x3, it's A, so minus 3A, moving to the right-hand side, we get 3A, 2b on the left-hand side, 2b over 6. We have minus 2b on the right-hand side as it moves, and the same denominator, and minus 2 that was simply there. That's the first variable, x1. And the second unknown, x2, see, if we have eliminated this minus 1, if we have 0 there, we actually do not have to express x1 using 3 variables. We don't need to use x2 for the first one. Otherwise, if I have this complete row here, I would need to express x2 first, and then use x2 also to express x1. That would be clumsy. That would be a lot more to write. But this way we see evidently from this equation or from this row, so these two are actually the same. From this we see that x2 will be on the same line with denominator 6. We will have minus 3a minus 8b plus 16. If you want to write 16 first, that's not a problem. And so now we can say, for instance, if we choose, that's the general solution, x1, x2, x3, and x4, these are all expressed using 2 random constants a and b. 2 of them because 1 would not be enough. And this is the indicator of how many constants may we choose. We have n variables, but we have enough equations only for 2 of them, which means the remaining 2 can be chosen freely. That's the meaning of the rank, of this rank thing and subtraction. We have 4 variables, but the rank means equations, meaningful equations. There are only 2 meaningful equations. So 2 variables are missing the necessary equations to determine them. That's why we can choose 2 variables freely. And then particular solutions. So this is the general solution. Everything is expressed in terms of A and B. And the particular solution you can choose, for instance, A is 1, B is 1, and then you might have anything else. So if A is 1, for example, and B is 1, then x1 would be 3 minus 2 is minus 1 over 6. And x2 would be minus 3, that's minus 11, plus 16 is 5 over 6. For example, that is just one possible particular solution. The general solution actually tells us that there are infinitely many of them. Depends on how we choose A and B. Infinitely many combinations and possibilities. So in the unit test, if you are asked to write one particular general solution and 1 or 2 particular solutions, that will be part of the unit test. Gauss methods, if there are these general solutions and particular solutions, you might be asked to find the general solution and write down a couple more things, that is a couple of particular solutions perhaps. Now, if you were asking anything, just a moment, I will increase the sound of my computer. I didn't hear anything at all. So, questions or problems?
ഇത് ക്ലാസ് കൂടും കേട്ടോ.
Oh,
സച്ച് നീ നീ എന്താ
okay, if you are talking among yourselves, who is talking not to me? Please switch off your microphone. I cannot do the lecture if you are talking. It's exactly the same as noise in the class. It's actually more distracting. If there are questions about this, then of course you're welcome to switch on the microphone and just ask. Or you can write your question in the chat. I have my second computer open. I can read the chat. But please, if you want to talk among yourselves, send private messages. But that means you are distracted from the lecture. All right, so we are moving now to actual vector algebra, back to vector algebra. As I said, in the unit test on Friday, I repeat, you will have 40 minutes and 3 systems of equations. The first one will be for using Cramer's rules, that is, determinants. The second one will be to use inverse matrix method, that is, you will have to create the inverse matrix and solve the system. And the third one will be use Gauss method. It might be Gauss method works properly and you get the unique solution. It might be Gauss method gives you infinitely many solutions. It might be Gauss method gives you no solutions. Well, that means there's less to do, a little bit less to do. The transformations are still there. So that's that much about the unit test, and I repeat that you will be split into 3 groups. The unit test will be in 3 versions in 3 sessions because I cannot manage 60 plus people at the same time. So I will put a list of your timings online just after this lecture. Basically, no lecture on Friday, just the unit test. That is, instead of 90 minutes, you have 50. And that's why we can afford to shift the timing a little bit. Okay, vectors. What is a vector? What is a vector? What did you learn at school what a vector is? So most people would say this is a vector, right? That's what most of you would say. And we could put 2 letters. We could put names to the starting point and the end point. But in principle, most people say a vector. A vector is an arrow. Or if they are a little bit more clever, they would say it's a segment with an arrow at one end, or a segment with a direction. That would be, let's say, a more clever answer. So we denote vectors by marking the starting point, end point. So we can write vector is a b like this with an arrow above, or we might write a vector with a small letter, not capital letter, lowercase letter a, again with that arrow. Please, when you mark vectors, don't put those arrows in the middle of the vector. It's sometimes it actually creates misunderstandings. It might be misleading and you simply don't pay attention. I know that some of you are used to, for some reason, putting the arrow in the middle of the vector. That's maybe not the best idea. I know that in some textbooks, some authors prefer that kind of notation. But I would say maybe it's not the best. I will understand if you do so, but it's not the best idea technically. Okay, so what we think in advanced mathematics, what a vector is, it's displacement. So geometrically, yes, it's an arrow, it's a segment with a direction, but in principle, it's displacement in the plane or in 3D space. The geometrical interpretation, yes, we can show it with that arrow, how far and in which direction. But in principle, in mathematics, it's more likely to be a displacement than a plane arrow. That would be geometry. But this unit is called, if you paid attention, it's called vector algebra. Why so? That is interesting because vector algebra is somehow the bridge between geometry and algebra. We can deal with problems of geometry using algebra, and that's why vectors are so very useful. A vector is a displacement in the plane, so actually what I mean by displacement is a vector shows that if I start at this point and end at this point, then this is my total movement. Because of course we understand when we move from one point to another, I could move by whatever route. But a vector tells me that what counts is where I started and where I ended. For example, I could leave work in the afternoon and go home, but I would like to take a walk. I would like to make a longer route. I would like to visit a grocery store or a supermarket on my way. So actually, I'm not going directly in a straight line. More so, the streets generally don't make me go in a straight line, but the vector discounts all this route, that all this diverting in different directions. A vector counts only I started here, I ended at B, so my displacement is the vector AB, no matter how I move, if I start at A and end at B. And in physics, of course, well, yes, geometrically, the directed segments, as we already said. But in physics, also we have physical properties for vectors. Force is a vector because for the force, we need to know, first of all, how strong that force is, but also we need in which direction this force works. With velocity, for example, when we consider movement, we are interested in how fast we move, but we are also interested how quickly we move. If I leave work in the afternoon, it's of course important in which direction I go if I want to reach home. So vectors have length. Geometrically, yes. Physically, it would be the strength of the force, it would be the velocity, and of course the vectors have direction. And the length is also sometimes called the magnitude of the vector or the absolute value. The magnitude of the vector. A scalar, as opposed, we already mentioned in matrix algebra, a scalar is a number as opposed to vector and as opposed to a matrix and opposed to many other things. So in principle, when I talk velocity and speed, speed is a scalar. For example, 60 kilometers per hour. That's speed, that's a scalar, that's a number. However, if I say my velocity currently is, at this moment, 60 kilometers per hour going northeast, then that's a velocity, that's a vector, that's a scalar, because it also involves a direction, not only the numerical value. So magnitude, of course, is a number, also sometimes called modulus, and geometrically it shows as length, but as we see in physics, in different physical quantities, and in other things, there are also, yes, vectors in economics. They are not physical vectors, and no, they are not geometrical vectors, but things that we can actually manage as vectors, and in many other areas, in fact. A vector could be anything, not necessarily a very specific physical or geometrical thing. The vectors are of three kinds: free vectors, sliding vectors, and fixed vectors. The vectors we consider will be mostly free. Free means that if I look at this vector I drew there and I drew it somewhere else, I am not saying A and B are equal vectors. Okay, I have I have slipped with the direction. The direction is not ideally equal, but in principle, if I have drawn equal vectors in mathematics, I can say, oh, it's the same vector. It's simply placed somewhere else. In other words, I can take a vector and move it along the plane or the space and put it wherever I like. So in principle, when I say a vector lies in the plane, for example, my yellow vector AB is in the plane of your screen and my screen, right? But I could imagine this vector coming out of that plane, being parallel to the plane, somewhere in the space between me and the screen. As long as it keeps the exact same direction, I would still say this vector is in the screen plane because it's free. I can take it and I can move it without changing the direction of the vector and place it in the screen plane. So this is what we think in mathematics. Vectors are free. I can take it and I can put it anywhere, and it's still the same vector. In physics, they use sliding vectors and fixed vectors as well. A sliding vector is a vector that is fixed on a certain line, that it can slide back and forth. It can slide back and forth, but only along this line. This is evidently linked to physical things, for example, moving along a track. Or for instance, you are pulling a toy car horizontally by a string. Okay, I know these days you have something that you can actually do it from a distance, radio conductible things and all that. But basically, if as long as you go along a track, for example, you have a ball and an object on a string, for instance, or on a wire or on a rod, it can only move in one direction. So if the speed is constant or the force applied is constant, it's a sliding vector because it's fixed to a line. And fixed vector, of course, is a vector that cannot be put anywhere else. Well, for example, if you want to get the same effect, exact same effect, when you want to push a door open, there's a certain point where you have to apply that force. So fixed vector, or when you have, for example, an object moving under the influence of, for example, it's being thrown horizontally, but it also moves under the influence of gravity, for example. Those two forces, for example, at the moment I throw this object, they are fixed to this object. They cannot be put anywhere else. So fixed vectors are generally, for example, forces that work on a certain object, for example. But as I said, yes, that's what you might see in physics. These vectors are something you might see in physics. In mathematics, we will consider all vectors free, unless, of course, the problem states something else. And so, okay, sorry, it's doubled. I don't know why my slide is doubled. That's not the thing. Types of vectors. Okay, collinear vectors. Two vectors are called collinear if they are parallel to the same line. So I would have two collinear vectors. Okay, let's make them yellow. So one parallel to this line, another parallel to the same line. We don't say parallel vectors, we say collinear vectors. Here. So on this line, the two vectors that are on the same line are also called collinear. So collinear vectors are what we normally would say parallel. So they are denoted by the parallelity sign, by the symbol of parallelity. This tells us nothing about going in the same direction or going in the opposite direction. So if we call two vectors parallel now, the two parallel vectors, actually it means they do go in the same direction, and we mark them as A and with these arrows going in the same direction. Erase, 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 wrong arrow. So we would have two vectors going in the same direction. This would be parallel. And then we have anti-parallel vectors. So if a vector goes in the opposite direction to the other, for example, this would be vector C, this would be vector A, this would be vector B, then I can write that vector A is anti-parallel. That means they are collinear but going in opposite directions. So this is how we can indicate directions for vectors in mathematical writing. If the directions parallel, anti-parallel, that is same, opposite, don't matter, we say collinear vectors, we don't say parallel, we say collinear vectors, and we mark them with a normal regular sign of parallelity. So this is something perhaps new. Parallel and anti-parallel are two different things, but they are still collinear, that is parallel in our old understanding, in our geometrical understanding. But vector understanding is parallel and anti-parallel. Equal vectors, as I said, sometimes we do need to discover that two vectors are actually equal. I already mentioned that a vector is free. It could be placed anywhere. But sometimes in a drawing, in a sketch, for example, if we have a parallelogram, we could say that the opposite sides are equal vectors. The geometrical interpretation, it would sound very strange to say it is the same vector, because we geometrically we think the segments are congruent, the lengths are equal, and then saying equal vectors seems natural, the natural thing to say. The two vectors on the opposite sides, if they go in the same direction, are equal vectors. However, if necessary, I can use the idea, I can say vector, a free vector, okay, I take this vector and I put it somewhere else. I take, for example, this vector and I put it somewhere else. I move this vector or I just place this vector somewhere else. And say it's the same vector, I only place it where I need it. That's also something we can say. So equal vectors, of course, are parallel and have the same length or same magnitude. That's, of course, the natural understanding of equal vectors. But yes, the direction is important. They have to be parallel, same direction, and equal magnitude, same length. Only then we can say that they are equal. Coplanar vectors in 3 dimensions. Coplanar vectors means the 3 vectors are parallel to the same plane, or they can be put in the same plane. Remember, being free, I can have 3 vectors in space, and they are called coplanar if we can put them in the same plane, move them down and put them in the same plane, for instance. So they don't have to be originally placed in the same plane, but if they are parallel to the same plane, then we call them coplanar. I might make a little bit of sketch. Suppose this is the plane alpha, for instance, and I have one vector, another vector, and maybe a third vector. So these 3 vectors are coplanar if I can move all of them and place all of them in the same plane. So they don't have to be at the same height above this plane, right? In this case, it looks like the first 2 vectors, let's say vector m and vector n, they look as if they are in the same height. So they are generally, evidently, we can imagine a plane passing through this, and we could imagine that the vector p is a bit higher, and so the projection line goes a little bit longer, it's a bit above, although it might not look like this because, you know, it's difficult to depict a 3-dimensional situation in a 2-dimensional picture. But if we can move all these vectors vectors down so that they are in the same plane, then they are coplanar. We consider them as denoting the same plane, being in the same plane. It's not always the case. It's not always the case. Two vectors are always coplanar. We can always find some plane that actually could contain both these vectors. Three vectors might be coplanar, might be not. Imagine that we have two vectors in the same plane, but the third vector, imagine a third vector coming out of this plane towards you, for example. Very typically, the system of coordinates in 3 dimensions. This is the three vectors defining a system of coordinates in 3 dimensions are definitely not coplanar. We have, let's say, the xy plane, and the vector defining the z-axis actually goes out of that plane. So coplanar vectors are always in the same plane. We will discuss those in a little while, maybe next time. Unit vector. A unit vector is a vector whose length is 1 unit, whose magnitude is 1 unit. By the way, magnitude is generally written using the modulus sign. Magnitude is written using the modulus sign, or the length. So I could say the length of the vector AB, similar to the distance between 2 points. The distance between 2 points would be written simply AB. So if I stress that this is about vector length, I simply put that vector sign above it. But yes, in principle, you may omit because it means the same thing. The distance between the points A and B is basically, in principle, the magnitude of a vector. And we use the modulus sign to indicate it. So a unit vector means that the length, the magnitude of this vector is 1 unit, 1 length unit. The most famous unit vectors, perhaps you are already familiar, in the 3 dimensions. I know I'm drawing a lot on this, but I would hope that we can get to the point. So if we think of the 3-dimensional system of coordinates, the most famous unit vectors would be the unit vector I in the direction of the x-axis, the unit vector j in the direction of the y-axis, right? And the unit vector k in the direction of the z-axis. So these are the most famous unit vectors, but we will use also others. We will have a look at some others as well. Maybe not famous ones, but basically these are the ones that we use often. The unit vectors along the axis, length is 1 unit, but sometimes we need to find the unit vector parallel to the vector c, for example. Finding the unit vector parallel to the vector c. That means in the same direction, but look at the length. The length has to be 1 unit. Zero vector or null vector, that's very strange, because for the zero vector, it seems that it's the vector AA, meaning the starting point and the end point is the same. For example, my complete total displacement during the day, I leave home, I go to work, I go to the supermarket, food shopping, and then I return home again. My total displacement is the zero vector, because in the end of the day, I'm back where I started. So zero vector as such is of course not important. What's the use of displacement that doesn't happen? So on its own, as alone vectors, the zero vector, we denote it usually by 0 with an arrow or O with an arrow. You can read it whichever way you like. 0 with an arrow or O with an arrow. Zero vector, in principle, is not so important as a vector, because it's like a vector that didn't happen. We are at the point A, we want to move somewhere, and we don't. The zero vector, the very strange idea of zero vector. However, it's more important in vector algebra, just like with numbers. The zero number as such is not important, but sometimes as a result, sometimes it's simply needed as something that describes a descriptor of something. As such, zero, nothing. Why should we care about nothing? It's important in another sense to describe something, to describe a situation perhaps. And similarly, the zero vector describes a situation where generally, geometrically, we return back to the same point. Scalar multiple. Now operations with vectors. Just a moment. Just one moment. Sorry. I needed to do this. Yes, I need to follow the time, so I had to exit the full screen in my other computer so that I can check the time. Okay. So now, vector algebra as such. If we deal with vector algebra, we have to think about algebraic operations. And vector algebra, in principle, we could think, let's say scalar multiple. What happens when we want to multiply a vector and a scalar? First of all, it is a vector, but what kind of a vector? Let's suppose we have a vector, let's say A, and we want to multiply by a number. So what would a vector, for example, I don't know, 3A look like? We understand? Evidently, we would put these three arrows one after the other, triple A, so that means it should be in the same direction. Okay, I'm not seeing what I'm sketching. 3 times longer, evidently, 1, 2, 3, right? And going in the same direction. If I want to write minus half vector A, what would that look like? It would be half the length, and if it's a minus, it would go in the opposite direction. So in principle, in this case, I can also say that minus vector A, that is minus 1 times vector A, which means it is simply the opposite vector. Simply the opposite vector going in the opposite direction, so anti-parallel, but same magnitude. So multiplication by a number for vectors is actually important. So we write vector B is k times vector A, and now we can make some conclusions about the direction, about the length, and so on. So we would say that the resulting vector, as we saw, is, first of all, the magnitude. It is k times longer, but magnitude can only be positive. Therefore, we also take the modulus, where we also take the absolute value. We also take the absolute value of the magnitude of the number k. The magnitude of vector A multiplied by modulus, the absolute value of the scalar factor, scalar multiplier, because magnitude can only be positive. So for example, this vector minus 1/2 A, the magnitude is half of vector A magnitude. We don't say that it's minus 1/2 times longer or minus 2 times shorter. We generally use only positive factors. So the magnitude, this is an important part, that we use k using the modulus, using the absolute value. Direction now. We already saw if the k value is positive, then the direction is parallel to A, same direction. And if k value is negative, the vector is anti-parallel, that is in the opposite direction. And of course, if we have a zero vector, which I missed out on in this slide, if I have a zero vector, then in principle that means that the 0 times vector A is of course the zero vector, magnitude 0, nothing happens. So this might also be something due to algebra. This doesn't need to have a geometrical explanation, but because vector algebra is algebra, we have to perform those operations. It's important that we have this zero element for vectors. and a theorem, going backwards. So the thing with definition of vector scalar multiple is if if one vector is another vector times a number, then the two vectors are collinear, because we see by the definition, by the description of the scalar multiple of a vector. This theorem goes backwards. If I have two vectors that are collinear, then it is possible to express one vector as a scalar multiple of the other. For example, we might say if this is vector A and this is vector B, and vector A is collinear to vector B in this case, then there exists some number k with which we can express one vector using the other vector. Doesn't matter which by which. So in this case, I would say that vector B is, that's how I tried to sketch it, minus 2 times vector A. So in this case, this number is minus 2. Which means that now we have two statements. Statement number 1, if we multiply a vector by a number, we get collinear vectors. The statement number 2, going back, if we have collinear vectors, then one is the scalar multiple of the other vector. So this is actually going back and forth. This is, logically speaking, if and only if. If vectors are collinear, then we can find such a k. If we have k and multiply, then vectors are collinear. This is the logical equivalence sign. Logical equivalence, logical identity, and we say it as if and only if. It works both ways. If we multiply a vector by a scalar, we get collinear vectors. But also, if we have collinear vectors, then we can write it using this scalar multiple. These cases are identical. In other words, multiplication of a vector by a number is in principle identical to finding a collinear vector. It's the same thing. Only one thing is geometrical. This is geometry, and this is algebra. So we are actually demonstrating a geometrical thing using algebra, using the idea of multiplication. This is the main meaning of vector algebra, to translate geometry into the language of algebra. I know that many people don't particularly like geometry because it involves proofs, it involves logic, which, if taught too late, is rather difficult to master. And so we have to pay attention to these logical things. I will do that. The sum of two vectors. Yay. So let's start with the triangle rule. Suppose we have a vector A and a vector B. So let me see, I don't remember. Okay, right. I didn't put any letters. I will put them now. So let's suppose we have a vector A and we have a vector B. And suppose we simply take the free vector B and place its starting point at the end of the vector B. So the starting point, or we say initial point, starting point of the second vector is the same as the end point of the first vector. So we could say A, B, and we could say B, C. So we can say A plus B is some vector C. And basically the definition is that this vector C, I'm marking it in red, is this. The vector A plus vector B. Because, why is that? What's the easiest explanation? The easiest explanation is, remember, vector is a displacement. So if I go from point A to point B, and then from point B to point C, two subsequent displacements, the total displacement is from A to C. So this is how we add vectors. AB plus BC is AC. The important thing is putting the vector one after the other, directly at the end. Now, the natural question is, of course, does it matter the order of the vectors? Remember, addition of numbers. With numbers, we would say 2 plus 3 is the same as 3 plus 2. Is it the same when we do vectors? Is A plus B vector the same as B plus A vector? In principle, if we think about this, think about blocks in a city, for instance. If you think about city blocks and streets, so if I want to go diagonally, I have to walk along the street. But perhaps I could walk along this street, not go straight and then right, but go first right and then turn left to reach that diagonally opposite corner. And if we remember basic geometry, if we place vector B not at B but at A, so that both vectors start at the same point, then in principle, then place vector A at the end of the vector B, then in principle, because we get a parallelogram, because the sides of a parallelogram are congruent and parallel, which means the vectors actually, depending on the placement, form a parallel, then of course it's obvious the diagonal is the same, of course. Whether I move through side AB and then BC or through side AD and then BC. So yes, in principle, we see that A plus B in vectors, a property of vector algebra, is the same as B plus A. This is a very typical property for all algebras. Yes, we have many. Algebra of numbers, algebra of matrices, now algebra of vectors, as you see. So basically this commutative rule, that is, we can exchange the order of addition, is a basic thing for any algebra. And so we have this rule, and this basically is the base of the parallelogram rule, because now we see if the two vectors are starting from the same point, basically all we need to do is complete the parallelogram. So the parallelogram rule would be, if we start at the same point, we could call it O. Now I'm changing the names. That's why I'm having a different diagram, a different picture. So suppose that one vector is OA, the vector A is OA, and vector B is OB, that is starting at the same point. Then, in principle, what I need to do is complete the parallelogram, draw some parallel lines, look at the parallelogram, and say, oh, all right, it's the diagonal. The sum is the diagonal of the parallelogram, starting at the very same point. So the parallelogram rule, okay, I wanted red, sorry. I'm trying to get the correct ink. Red, please, red, please. A plus B is the diagonal that basically it starts at the same point. So the parallelogram rule for adding vectors is this. The parallelogram rule, you see, it's more convenient in physics, because if we have two forces acting on the same object, then the resulting force, the sum of these two forces added vectorially, added as a vector, is evidently to be found by the parallelogram rule. So the sum is actually the diagonal of the parallelogram, which starts at the same point. So in physics, parallelogram rule is more convenient. In geometry, well, the triangle rule is good because we can use it also for many vectors. It also works for many vectors. Let me check what's the next. Oh no. So for many vectors, it simply means that I can take vector A plus vector B plus vector C again plus vector D, and the resulting vector will be, of course, from the beginning of the whole thing to the end. That would be the sum, A plus B plus C plus D. The sum of several vectors. Okay, head to tail. You can say head to tail, but you have to understand what is head and what is tail. When I think about this, I move along the vector. My thought would be head is the end point, the end with the arrow. But actually, head to tail is yeah. That's interesting, because in my understanding, if you mention head to tail, it would seem that actually I go walk head first. That's an interesting interpretation, because it depends how you are taught. So if head to tail causes the correct association in your mind, if you think of head as the point and tail as the arrow, then it might work. Then you would say yes, that's right. That could be. All right. So if you have several vectors, then parallelogram rule is actually not convenient. But the polygon rule, if you say, the triangle rule repeated, or triangle rule simply generalized for many vectors, works very nicely for some of several vectors. We will use these a lot, because when we have to express some vector knowing some given vectors, we will follow different routes. And actually, this means that following a certain route basically means adding those vectors. Now, the difference of vectors. There are again different kinds, different ways of figuring out the difference of two vectors. So from the triangle rule, if we think about difference of two vectors, if we think of difference of two vectors as the sum of the given vector and the opposite vector. So let's say this would be the starting one of the vectors A, the first vector, and we have to subtract vector B. This means I actually have to use vector minus b, the opposite vector. And that means I take the opposite to the vector b. And I write, all right, this is the vector minus b, going in the opposite direction from the end of A. And that makes me see, why is this not working properly? And that makes me see that, in fact, this is the difference of these two vectors. If I sketch it this way, so adding the opposite, but you have to remember to take the opposite vector. The direction of the vector is very important. So in principle, I can find the difference of two vectors by simply adding the opposite vector. But from the parallelogram rule, it's a little bit different. So let's see what happens if you compare my previous picture, this one. So all right, we have this parallelogram, we have these two vectors, and we, in principle, if we simply change the order, we take minus b first, and then add vector A. Remember that, yes, we may change the order of operations. Yes, we are allowed to do this. So if I take vector minus b first and vector A second, well, you see it's the same. But it's this vector connecting the endpoint of B to endpoint of A. That's a somewhat crazy notion. So if I have vector O, I have OA, that was the vector A, and I had B, that was the vector B, in the second kind of picture in the previous slide, then we actually see that vector OA plus vector AB would be vector OB, and then vector OA minus vector OB is minus vector AB, that is BA. This is simply using algebra without picture. I will talk about it in a moment. So from the diagram, from the picture, we actually see that vector OA minus vector OB is vector BA, that is from the end of the second vector to the end of the first vector, that is A minus B, is actually from end of B to end of A. See, going sort of backwards, as if, well, if you simply look at the letters, if you don't look at the picture, if you don't look at the diagram, the beauty of this is it doesn't matter what those vectors actually are. If the configuration is right, it doesn't matter which direction they go, what the length of these vectors is. It always works. It's algebra. It's just algebra. So this is the interesting thing. You have to pay attention to the direction from the end of second vector to the end of the first vector. If we use only algebra and not the picture, then again, this can be written without seeing anything from O to A and then from A to B. Of course, the sum is the resulting vector is from O to B. That is from the triangle rule. If we put vectors one at the end of the other, the thing that matters is, of course, that A, see where the first vector ends, the second vector begins. So when we add these two vectors, we go from the beginning, which is O, to the end, which is B. And I don't need to see anything. Similarly, I could write, for example, A, D plus dm is, of course, the vector am. I don't need to see what those vectors are. From A to D and then from D to M, the total displacement is from A to M. And that is another thing why vectors are very good. Sometimes you don't even need to see the picture, but you can do these geometrical things. And so, doing algebra, I could, for example, subtract OB from both sides and subtract AB from both sides. In other words, using the rules of algebra, I can perform this and express subtraction of vectors. I can express subtraction of vectors. Simply, if I follow algebra, I start with this very abstract, with this very abstract statement, which doesn't need my seeing what it is about. I don't need to see the vectors as they are. I only need to see the connection from O to A, then from A to B is O to B. And then I do plain algebra. This is algebra, as if you do with numbers. Exactly the same thing if you do it with numbers or with variables, perhaps x, y, z, if you like. So you can actually think if x plus y is z, then you can think x minus z is minus y, just like you do it with normal algebra. And now, okay, minus y minus ab, it means we have to change the direction of the vector without seeing anything at all, just using algebra. This is the true great value of vector algebra, vector geometry. Okay, going back. So in principle, the parallelogram rule. Now I'm going to erase all ink at the moment from this slide because what I want is to show you what's going on here. So if I have two vectors starting at the same point, then the sum of these two vectors is the, let's call it the main diagonal. The main diagonal in the sense that it starts at the same point where the two vectors start. Vector A, vector B, if they are starting at the same point, then the sum of these two vectors goes along the diagonal starting in the same point. However, if I want to subtract these vectors, it is the other diagonal of the parallelogram. This is A minus B, going from B to A. Going from B to A, and we could call this C if you like. So OACB is the parallelogram. So in other words, if you have two vectors starting at the same point, then when you complete the parallelogram, the sum is the diagonal going through from the same point, and the difference is from the second to the first. So if this was vector A, this was vector B, then this difference, A minus B, goes from B to A endpoint. So this is the most important thing probably in vector algebra before we start, let's say, product multiplication of vectors. This idea of a parallelogram. Now next, vector projections. Vector projections. Okay, I forgot to use animations for this one. Okay, so let's suppose we have a line or an axis u. The axis u, this is an interesting thing. It's not a vector because a vector has a length, but we would think it's an axis, like a line with a direction, like the x-axis, the y-axis, perhaps some other axis. That is a line with a direction. So this means line, not a segment, but just a line plus direction. That would be an axis. And we have a vector somewhere, and we project this vector on that axis, as in geometrical projection, as in light shining down vertically, and the vector is throwing a shadow. The vector is throwing a shadow. There are different kinds of vector projections. The vector geometrical projection is this vector A prime, B prime. That would be a geometrical projection, and it is important in physics. Geometrical projection is important in physics because, in principle, sometimes we need to project a force. That is, for example, a child is pulling a toy car and the string goes up. The string goes up. So actually the force vector is going this way as the child is pulling it, but the car itself moves this way. So we need the projection. We need the projection of the force on the horizontal line, for instance. This is the meaning, this is the need for these geometrical projections. But we in mathematics will deal a little bit different aspect of this, the geometrical projection, not the vector geometrical projection, but the algebraic projection. And that will mean that the projection of the vector AB on the axis, on the line u with the direction is, in this case, the vector A prime, B prime magnitude, the distance between these 2 points, the length of the horizontal displacement, if you like, only the length. This is in the situation where the angle between the vector and the line is acute. An acute angle, that is an angle less than 90 degrees. I'm saying it because some of you might have some problems with English, so the English terminology, acute angle is less than 90 degrees. Acute angle, okay. So if the angle between the vector and this axis is acute, then we have this number. That is, if actually the projection, the geometrical projection, the geometrical vector projection is parallel to the line u. That is the angle. This angle is acute. On the other hand, now if we have this other picture, in other words, if that angle is obtuse, so obtuse is greater than 90 degrees. Of course, it's also less than 180 degrees. But we are talking about normal geometrical angles. So acute angle less than 90, obtuse angle greater than 90, but less than 180. And so if this angle, as we could see, is obtuse, the angle between the two directions is obtuse, which means that when we project this vector AB down, when we project this vector AB down to that line, then the geometrical projection, the vector A prime, B prime, is in the opposite direction, is anti-parallel to the line U, to the axis U. The angle is obtuse, it means this situation is anti-parallelity. And in that case, we take the magnitude of the projection, but with the minus sign. So in principle, we are looking at the component or the projection of this vector in a certain direction. It could be negative, but it's a number, positive or negative number. In other words, if I have a vector projected on the, let's say, x-axis, then if I project it, let's say this would be, let's say, the direction of the, let's say it's the x-axis, then the projection, we are already moving towards coordinates, the projection would be the length of this segment. But if a vector is projected and we find out that the projection geometrically goes in the opposite direction, then we get a negative number. It's like the displacement of the vector, the component in the positive direction, or the component goes in the negative direction. Positive displacement in this direction or negative displacement in this direction. But please remember, we are talking these projections, this means a number. This means a number. We are not talking vector projections. You need vector projections in physics. But in mathematics, we will deal with these numbers because they will be very important next time when we deal with coordinates of vectors. So next time, that will be Monday. And we also can use this actually very excellent interpretation about the cosine. Now I'm going to erase my scribblings so that I can focus on this cosine thing. So I need a pen that would be visible there and there. Okay, I'll take the blue pen. Okay, so we might think, so in this case, this is the angle alpha. And in principle, if we consider this triangle ABC, this is a right triangle. And from school, of course, you know that cosine of alpha, okay, now I want it here, that cosine of alpha is actually the adjacent side AC divided by hypotenuse, which is AB. We are talking about length, right? So this means that AC, this length, is AB, that is the magnitude of the vector, times the cosine. So we get this idea from the right triangle. Projection is actually the length of the vector, the magnitude of the vector, times cosine of the angle this vector is forming with the axis U, with the line U. Similarly, in this case, we would say, all right, if we consider this angle, then we, in a similar way, but we get a positive number. However, the actual angle alpha is this, and it is an obtuse angle, and we know that that angle has a negative cosine value. And in this case, the same thing works, because now here we have this negative projection. That means the magnitude times cosine. In this case, cosine is actually negative. Cosine is actually negative because the angle is obtuse. So this is the universal formula for the projection. This is the universal formula. Meanwhile, at the moment, we think, okay, if the directions form an acute angle, then the projection is positive, and if they form an obtuse angle, then the projection is negative. But we can combine these two ideas, and we can write a general statement. The projection of a vector on a line equals the magnitude of this vector times cosine of the angle between this vector and this line. So this is something, again, important for projections, important for vector coordinates. We will deal with this, well, hopefully next time. And now some exercises. Let's express. So we have two exercises. This is number 1, this is number 2. I put them both on the same screen. Express the vectors AB and AD in terms of vectors AC and BD. So how do we express vectors? It's okay, we have about 5 minutes to go. So let's have a look at this expression thing. And the next time we will need to do more exercises before we start actually on the coordinates. So, all right, just remember that when you have a parallelogram named by its vertices, put the vertices in the correct order, A, B, C, D. It doesn't matter whether you go clockwise or anti-clockwise, they have to be in order. You cannot do A, B, C, D in this order. Makes no sense. They have to be in the correct order, because otherwise it won't work. Nothing will work. So vectors AB, this should be expressed. The vector AB and vector AD should be expressed. But we are given vectors, and I will mark them in yellow. Vector AC is given. We are supposing we have the vector A, and vector B is BD. It's also given. This vector is also given, vector B. But we have to express the vector AB. How should we go? How should we do this? In principle, that would be something. The best way of thinking for this would be, how can I get from A to B only moving through the yellow lines? How can I express the vector AB? Using yellow vectors A and B can be translated. How can I get from A to B only moving along the yellow lines? Because those yellow lines represent the vector AB. In principle, let's remember, it's a parallelogram. This is a parallelogram. This means that the intersection point of the diagonals is actually their midpoint. So in principle, I could say, evidently, vector AB could be written as, we could go from A to B through AO, from A to O, and then from O to B. This is moving from A to B only along yellow lines. That is the beauty of vector addition. We can choose our route along given vectors. And so let us see, vector OAO is actually half of vector A. And vector OB is also half, but see, it goes in the opposite direction. Its length is half of B length, but it goes in the opposite direction, and that's why I have to say it's minus half of vector B. And that's it. And that's it. So we consider moving along the vector A, but only halfway, and then opposite to vector B, opposite direction to vector B, but also halfway. And that's the vector AB now. We have expressed, we have completed, let's say, this vector. And what about AD? To go to vector from A to D, I can say from A to O, and then from O to D. Again, it doesn't matter what the actual shape and size of the parallelogram is. And so I see from A to O is still half of A, and from O to D is now positive half of B, because now the direction is correct. Another way of doing this might be just like writing a system of equations. So AB plus AD is vector A, and vector A, so B goes from B to D. That means I have to write AD minus AB is the vector BD, that is B. And then solve it as a system of equations. So if you add the two equations, you get two vectors AD equals A plus B, and then take half of it, and if you subtract these two equations, you get two AB vectors equals half equals A minus B. So there are options now. Translating geometry into algebra, we can use basically all the rules of algebra for dealing with vectors. And now it looks like it's time to end this. So for people who joined late, in a few minutes I am posting a list of unit test groups in Ortus. Please also read the information. Make sure in advance that you adjust the camera. I know it's not easy, but you adjust the camera so that actually you are visible, your head and your hands. Make sure you know how to create very quickly a PDF file from images. So most smartphones have an application, Scan, and creating the PDF file automatically. But you have to name this file. Don't upload it automatically. Name this file with your own name when you upload it to assignment. Also, make sure that you know how to find assignments in Ortus, your assignments, and in the correct assignment. Well, you can have a look at the homework assignment folder. We will be able to find it.
Hello, ma'am.
Yes.
I have a doubt, but not in this class session.
So please, can I?
Ma'am, the third question in assignment, we couldn't verify the result of definition of inverse matrix.
What do you mean you can't find it?
Like, I couldn't understand what it means. Verify the result of definition.
Assignment in Ortus. Investigate your Ortus. You haven't paid attention to Ortus. You haven't investigated all options that are there. So you have 2 days to find it. Assignment is a special folder in Ortus. It should be in mathematics course, in mathematics page. You should be able to find it. But use a computer. Don't use your phone. Use a computer to find it. It's there. It's a special folder. They are called assignments. In general, they are called assignments. But the title of that assignment is home assignment number 1. But if you just put in search in Google, not in Google, in your Ortus, if you put in the search box assignments, it will show your assignments. The assignments will have different names because in all subjects, there are different assignments. So I have one assignment at the moment, home assignment number 1. For the unit test, I will have another assignment, unit test number 1. the upload time is limited. So for the home assignment, it's by Friday evening. But for the unit test, it will be closed 10 minutes after the end of the writing time. So that's why I'm saying you need to practice. You need to make sure you can find everything in advance. That actually was a very good question that you asked me, because I am reminding you, make sure you know where it is and how to find it. I will also create this assignment. You won't be able to upload anything yet, but I will create this assignment today, so you will be able to see it, so that you can find it, so that you know where and how, so that you can investigate a little bit. But yes, this is the first test for many of you. Some of you are familiar with the system and some of you are not. So you have time to investigate a bit. And so make sure you also know how to make that PDF file. Please put the questions in the correct order. For example, you could take pictures of the questions in the correct order. That would be one thing where you don't need to change the order of images in the scan if you are doing the scan. If you are taking photographs, simply photographs, and then on the computer pasting those into PDF, that is possible. Then you can adjust the size, you can stretch them a little bit so that they are big enough, so that I can read them. They need to be big enough. You need to adjust the contrast probably and the lighting so that I don't get all those blue or yellow pictures, white balance. If you like to take pictures with your phones, you should know how to adjust them so that they look good, so that it's readable. Also, please write with a pen, not a pencil, because pencil written photographs are basically unreadable, and so on and so on. So make sure you investigate. You know, when you have finished, how to make your file quickly, efficiently, how to, let's say, make the image proper size. That is, if you paste it in the document, and then you can stretch the image a little bit, pull it a little bit, adjust the size so that it's not a small picture in the corner of a sheet, for instance, and so on. Okay. I will put my email address in Ortus. I will put it in Ortus, basically.
Madam, how much question do we have in exam?
Again, I've been talking about it all the time. I've been talking about the examination all the time and telling things all the time. It's not an exam, it's a unit test, so it's not a big exam. It's not a big exam. I have been talking about it all the time, which means either you were not here or not listening, or I don't know what, or you came late. 3 questions, 40 minutes, plus upload time, extra time, 10 minutes. So basically, if you practice in advance how to make that file, how to upload the file, and if you, for example, you see I can do it in 5 minutes, then you might have a couple of minutes extra writing time, of course. But basically the writing time is 40 minutes. I will share the questions on the screen. There will also be the necessary information, like a small formula sheet, or information about matrix algebra, about linear algebra, so that you don't have to go wherever. So the main formulas, the main information will be also on the screen at the same time. So half the screen with questions and half the screen with that extra information, so that you have everything on the screen. You don't have to fumble around. And then when you finish, you take pictures of your work. As I said, best of all, in the correct order. Then you don't have to think much. Please make sure they are in good focus, because people who do it for the first time sometimes don't pay attention to focus, to lighting, to readability. So this is something, please understand that in Ortus, when I mark the papers online, when I mark your tests online, I cannot change the image size. I cannot zoom in. The Moodle doesn't allow it. I cannot rotate. So if you put the image sideways, it's just that I say, no, I'm not marking this. I'm not trying to stretch my neck in the wrong way. So please make sure that you do it in a readable way. That's what is important. And as I said, I will right now. Okay, I'm spending too much time. I don't have enough time to adjust the group lists. As I said, today I am posting the group lists. It will basically be a large Excel file where I have written at, for example, at 2:30 at the normal lecture starting time, there will be 22 people writing this test. Then 15 minutes later, the next group of 22 people, and then 15 minutes later, that is 4 and something, a little, 4, I think 4:10. A little bit later, then there will be the third group of 22 or 21 people writing this, because I cannot manage in an assignment and in an exam or a group or a test 70 or 60 people. That's why I have split you in groups. To compensate, you don't have any lecture on Friday, so you have only 15 minutes mathematics time. That's more or less it. I am reminding you in advance about academic honesty, because if I have the slightest suspicion, ask those who know me. If I have the slightest suspicion of cheating, and yes, giving your solutions to your friend also counts as cheating, you will not have any opportunity to retake this test. So please do your own work, show your all working, because not showing all work is one of the suspicious signals. So show all work, do all working. There should be enough time. There should be enough time. You are good enough and understanding enough. And this first test actually is, I think, the easiest one, of course, because it's the very beginning of mathematics. Did you listen, Mr. Lawrence? You didn't listen. I'm going to share the questions on the screen, along with extra information needed. So I think in the future I will not repeat anything, and those who don't listen, don't listen. All right, so now, please, people who have ignored elementary mathematics, that is, you didn't write the online test, you are supposed to come to elementary mathematics automatically. And I'll see people in elementary mathematics in some 20 minutes, evidently. So those who were not, let's say, obliged, those who have passed the elementary mathematics intro test are not obliged. It's not mandatory. So there are some people who simply